In this video, we're going to talk about geometric sequences. Our objectives are to find the common ratio for a geometric sequence, to list the terms of a geometric sequence, to use a recursive formula for a geometric sequence, and to use an explicit formula for a geometric sequence. Though specifically on this worksheet, we're going to talk about how to determine if a sequence is geometric and how to find the geometric or the general term of the geometric sequence, the nth term. I'm going to be using the calculator a little bit today for some of these things. So I've got that open here on the right. This is the official online calculator from Texas Instruments, which you can see if your school has a license to for you, or you can get a personal use license for $20 a year, I believe it is. So pretty inexpensive. So objective one here, to determine if a sequence is geometric, we're going to find the common ratio, because a sequence is geometric if the ratio between consecutive terms is always the same. To find the ratio between consecutive terms, we're going to take the term that's further to the right and divide it by the previous term. So we call this term an, we call this term an minus 1, and we divide an by an minus 1. So in this example, 12 divided by 4 is going to be 3. We're going to do that all the way along to make sure that we always get 3 for a common difference. So if I wanted to check some of these numbers that weren't so obvious, like 108 divided by 36, and then 324 divided by 108, and 972 divided by 324. You'll see we always get a common difference of 3. So that is going to be our R right there. So we don't always have to have a whole number for a common difference. It doesn't even have to be a positive number. It can be a negative number. It can be a fraction, a proper fraction, an improper fraction, a negative proper or improper fraction. We just don't want it to be 0, because that would be kind of silly to multiply by 0 every single time and keep getting 0, right? So we also really don't want it to be 1, because then we're not changing from term to term. So we want some non-zero, non-1 common ratio. So let's go ahead and look now at this next sequence, which starts at 8, then goes to 4, then 2, then 1, then 1/2, then 1/4. You probably could guess this if you just looked at it without them telling you, but each time we're taking a half of the previous term. So 8 times a half is 4, times a half is 2, times a half is 1, times a half is a half, times a half is a quarter, and they actually did the division over here on the first few terms to prove that. Make sure you do it on all the terms, not just the first few, because if any of them are different, like we're going to see below, then it's not geometric. So let's go ahead now and determine if this sequence is geometric. It's kind of the opposite of what we did up here, where we had 4, 8, 16. We're multiplying by 2, 32, 64, 128. So if we wanted to prove that to ourselves, 8 divided by 4 is 2. 16 divided by 8 is 2. 32 divided by 16 is 2. 64 divided by 2 is 2. 128 divided by 64. Sorry, I did that backwards, but 64 divided by 32 is 2. So we have a common ratio of 2 all the way along here. So this one here is geometric. Turn my pen around. Yes, R equals 2, right? So -2 times what gives me 6? That would be -3. But then it's going to be times -2 to give me 12. So this one is not geometric because this one has a ratio of -3 and then -2 and then -3 again and then -2 again and then -3 again. So not a common ratio. Now let's look at this. Oh, those are our solutions there. Okay, so now let's look at this one down here and determine if this sequence is geometric. -150, -30, -15, -5, -5 halves. -30 divided by -150 is going to be, that's, I want to hit math, answer the fraction. It's going to be 1/5. Then -15 divided by -30, I'll tell you, is 1/2. And then -5 divided by -15, that's going to be 1/3. 5 halves divided by 5, or -5 halves divided by -5 is going to be 1/2. So this is not geometric because you have different R values going on there. 8, 4, 2, 1, 1/2, 1/4. We've actually seen this particular ratio up above. So this sequence, 4 divided by 8 is a half, 2 divided by 4 is a half, 1 divided by 2 is a half divided by 1 is a half, 1/4 divided by half is a half. So yes, it is. R is equal to 1/2. In example 2, we're going to find the first 5 terms of a sequence whose first term is 3. That means A1 equals 3 and R equals -2. So 3 times -2 is -6. Then that -6 is going to go there, times that -2 is 12. 12 times -2 is -24. -24 times -2 is 48. Let's try this ourselves with first term being 7 and R being -3. So I'm actually going to let the calculator do this using a formula that we're going to learn down here. This is going to be 7 times -3 to the, and let's say x minus 1 to follow their formula. And I'm going to start my table, n equals 1, and automatically go ahead there. So we've got the next one is 7 times -3. It's going to be -21. -21 times -3 is going to be 63. 63 times -3 is going to give me 189. 189 times -3 is going to be 567. So I didn't want to do some of those big ones by hand. I let my calculator do them for me. So let's go ahead and let's talk about that formula that I just used in my calculator here, which is that each time we're going to be multiplying by the common ratio again, so we can use an exponential form. You probably have seen things in the form of like the population at time t was equal to P0 times some a to the t, something like that. And we're going to use that same kind of idea because this is exponential, either exponential growth or decay, depending on what this base is here. what R is. So we're just going to instead, remember a sequence is a function whose domain is the natural numbers. So instead of having an f of n or a p of n or something like that, we're just going to have an is going to be equal to, and we're going to have a1 times r to the, and because the textbook here starts its first term at 1, this is going to be n minus 1 because we don't want to multiply by this r the first time for a1. So we want that to be r to the 0 is 1 for a1. There's another way to write this if we want to start counting at 0 and use whole numbers instead. I'm going to use this model in our last example that we do today. And those are equivalent models because this one starts counting at a1, and this one starts its initial term at a0. So they're equivalent forms, but you just need to watch out what you're doing. We like to use this one a lot when our variable is actually time, or we have an t instead of an n because we like to start counting time at 0. Other things, or we're talking about production or something like that, we may want to go ahead and start talking about when we produce the first item because you may not want to talk about producing nothing. So, all right, let's do some examples where we find the general term or the nth term of a geometric sequence. So if we're given a sequence whose first term is 81 and the common ratio is 1/3, and we want to find the 13th term of the sequence. So a1, they've told us is 81, r is 1/3, and n is equal to 13. We're going to plug that into our general formula that they gave us, an equals a1 r to the n minus 1. And that's going to be that the 13th term here, a13, is going to be 81 times 1/3 to the 13 minus 1, because we're going to need to multiply by that 1/3 12 times. So I'm going to plug this in, just make sure we got the math right here. 81 times 1/3. I know you all like to do it this way, so I'm going to do it that way too. 1/3 to the power of, and then 13 minus 1, just like they have in the formula, right? And I'm going to get some crazy decimal that doesn't look like this answer here. I'll let the calculator change it back to a fraction for us. It's 1/6,561. If we wanted to do that a different way, by hand, we could say that 81 is 3 to the 4th, and we're going to have 1/3 to the 12th. So that's going to be 3 to the 4th times 1 to the 12th over 3 to the 12th. 1 to the 12th is just 1, so that doesn't matter to me. That's a big 1. 3 to the 4th goes into 3 to the 12th. 1/3 to the 8th, and 3 to the 8th is 65, 61. So you won't get the big, scary decimal and scientific notation that way. If you don't know, that means times 10 to the -4th, but we want exact answers when we can give them here. We don't want decimal approximations rounded unless it's a word problem that demands that we need to round it to decimals, like our last problem we're going to do today. Let's look at the sequence for part B here. 6, 18, 54, 162, 486, and 1458. Yep. So if we go ahead and we divide all those consecutive terms out, we get 3 for all of them. So we do have a common ratio of 3. And our first term is 6. They've got that listed there. So we're going to start with our formula an equals a1 to the times r to the n minus 1. We're going to plug in that we want a9 because we want the 9th term. And that's going to be 6 times 3 to the 9 minus 1. And that's going to be 6 times 3 to the 8th. Remember to do exponents before multiplication. So 3 to the 8th. And that's 6561 times my 6. It's going to give me 39366. So there you go. If we had typed it all in to start off with, 6 times 3 raised to the 9 minus 1, we would have gotten the right answer as well because the calculator knows order of operations. This calculator, not every calculator knows order of operations. So be careful if you've got a 4-function calculator that doesn't know order of operations. You need to do order of operations doing parentheses, then exponents, then multiplication and division, then addition and subtraction. To find our general or nth term, we're going to substitute in the constants that we know and leave the variables. So our nth term, an, is going to be equal to 6 for a1 times 3 for r raised to the n minus 1 power. So there you go. Let's practice a little bit more here. Let's find the 16th term of the sequence whose first term is 11. And the common ratio is -6. So 16th term, we want an is equal to a1 times r to the n minus 1. So a16 is going to be a1 is going to be 11 times -6 to the 16 minus 1. Definitely going to let my calculator do this one for me. 11 times -6 raised to the 15th power. And it's going to write this one, I'm pretty sure, in scientific notation. It is. So this is a16 is approximately -517203483. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. So there's still 4 zeros over here, like that. So it's approximately that. Or we could say a16 is approximately -5 point, wherever your teacher told you to round it to, let's round it to 2 decimal places, times 10 to the 12th power, right? In scientific notation, matters how many significant figures your teacher cares about. So there we go. This next sequence, we want to find the 10th term. So we want, again, an equals a1 times r to the n minus 1. We want the 10th term, where a1 is 9, and the common difference, or the common ratio here appears to be 2 to the 10 minus 1. So 9 times 2 to the 9th is A10 is 4608. Now you may remember this last problem here, this try it number 1. And this is from our first lesson where we just talked about sequences in general. And I told you that this particular problem, which I believe was the last problem on that worksheet, was going to be a geometric sequence. So a patient takes 30 milligrams, a 30 milligram antibiotic capsule at the end of every hour. The amount of antibiotic remaining in her body is only 90% of the amount in the beginning of that hour. The table below shows the amount of medication remaining in the body at the beginning of each hour. So at the beginning of hour 0, we have 30 milligrams, right? And at the beginning of after we've completed 1 hour, 27, the beginning of the second hour, at the time t equals 2 is 24.3, and so on. So this is a better way to write it. They had written this at the beginning of each hour, and they had said 1, 2, 3, 4, and 5. It's a little more confusing than saying how many hours had passed, which is what I did. And I said 0 hours had passed initially, 1 hour had passed, 2 hours had passed, 3 hours had passed, 4 hours had passed. It's normally how we're going to talk about it in medicine. So that's how we're going to talk about it here. And that forces us to use this idea here because we're starting with time is 0. So find the ratio of the consecutive terms. We already know what it is. It's right there in the problem. It's 90%. So it's R is 0.90. I rounded some of these things towards the end. So if we take 19.68 and divide it by 21.87, it's not exactly 90%, but it's within a tenth or even a couple hundredths of a percent because of rounding here. The reason I rounded it is because we're talking about milligrams of medication. We can only get so precise in our measurement of the milligrams of medication. So it's likely we're rounding to the nearest hundredth of a milligram because that's likely how precise our measurement is going to be. For find a formula for the general term here. So we just started there, but AN is going to be 30 times 0.90 to the, and I'm going to call this not N, but I'm going to call it T, where T is the number of hours that have passed. And how much medicine is left at the beginning of hour 7. So to go from at the beginning of hour 7, we're going to say that this is it 6? Let's just do this let's change how this is written. At t equals 7, because this is how it's usually going to be asked in your math class. So at t equals 7, t equals 12, and t equals 24. I'm going to let my calculator do this because this is very repetitive. So I'm going to come in here and I'm going to write the formula 30 times 0.90 raised to the x. And I'm going to use my table settings and I'm going to change this to ask. I'm going to go to my table here and say that I want to let it be 7, 12, and 24. And I'm going to look at the graph and show you what the graph looks like in a second. But we're going to see that at the end of, so I'm going to call it this A for amount, when t equals 7 is 14.35 approximately milligrams. I'm going to stay consistent with how many milligrams I'm going to use. The amount in the bloodstream at 12 hours is 8.47 milligrams. And the amount after 24 hours, time equals 24, is 2.39 milligrams. Again, rounding to the nearest hundredth of a milligram. I'm not using the rounded values to calculate. Again, I'm not explicitly going through recursively, I should say, each time, and going through A7 to get to A8, A9, A10, 11, 12, so on, by multiplying by 90% each time. I could do that, but I don't want to use, I don't want rounding error on top of rounding error on top of rounding error. So again, I just rewrote this problem to make it a little clearer in the terms of the way you're usually going to be asked it in a math class. So you don't have to think about, wait, at the beginning of the first hour is time equals 0. So that's how they wanted you to think about the first hour goes from time equals 0 to time equals 1. The second hour goes from time equals 1 to time equals 2, and so on. So at the beginning of the 7th hour is going to be raised to the 6th power, but we're not going to do that here. We're going to actually just say, you know, let's find it when it's been 7 hours. Or if we want to find it when it's 6 hours, let's explicitly state we want to find it when it's 6 hours, and it's that. So 6, 12, and 24 sound right for what they wanted us to do. And because those would be usual times that you would draw blood and find out the levels. So they're just being tricky when they say at the beginning of the 7th hour, that means 6 hours have passed. And this is 15.94. So okay, so hopefully that I don't ask you tricky questions like that. But remember that most of the time when we're doing these geometric sequences or geometric series, which we'll talk about next time, when we talk about series, that we're going to many times want to start looking at this when it starts at 0. It's more convenient for our formula for those series, definitely when we get there. All right, that is it for this time. We'll come back and we'll talk about arithmetic geometric series, as well as maybe some other types of series that you need to be aware of, and the notation for series when we do our next video. See you next time.